So now, the next topic, let's start with the limits. Okay. So first we have to understand what's the limits. This will be the base of our whole differential calculus. Our calculus has already started when we started with the chapter functions. But through limits, we will start with the differential calculus. I will teach you what is differential calculus later on. But first we must understand what is a limit. Now guys, see, limit as it is has no definition. Okay. If you just say a limit, it has no meaning. You must say limit of a function. Okay. Limit is only defined for a function. Okay. So let's see the definition of limit. The definition of limit says that limit of a function fx is defined as that finite value. It's defined at that finite value which the function approaches while moving in its domain in the neighborhood of a fixed point. I've double underlined some words over here. Okay, first word is that finite value, second is the domain, and third is neighborhood. Now these three terms are very important in the definition of limits and for the understanding of limits. Okay, how are these important? Let's see. Now let's suppose that this is our function. Okay, our function is moving something like this. And I have to calculate the limit of this function at, let's say, x is equal to a. So our fixed point in the case of this function becomes x is equal to a. Now I have to see the limit of this function. So by definition, let's see, what does it say? Limit of a function fx is defined as a finite value which the function approaches while moving in its domain. So if I have defined this function from here to here, the domain of this function will become this one. This region will be the domain of the function. Okay. Now domain is always seen by the x-axis. As we have already discussed, the domain is seen on the x-axis and the range comes on the y-axis. So the domain of this function is from here to here and the range will be this one. So this region will be the range and this will be the domain. In the neighborhood of the fixed point. Now what do I mean by the word neighborhood? Neighborhood means if I start moving across this function, okay, let's start moving from the function on the x-axis. Okay, as I am about to reach this x is equal to a, I want to know the value of this function as I'm about to reach the value x is equal to a. Okay. Similarly, if I'm moving backwards on this function, as I'm about to reach x is equal to a from this side, I want to calculate the value. Both these values will give you the limit. Okay. So as we are trying to approach towards x is equal to a, the finite value, now the value of this function at x is equal to a will be on the y-axis. The value of the function given by x is equal to a will be equal to the limit. Okay. So we can say that at x is equal to a, the limit will be fa. Okay. So fa will be the limit of the function as x approaches a. Okay. Now these terms are very important. Approaching, okay, neighborhood and domain. We cannot talk about limits if the point which we're talking about, it's out of the domain of the function. If the point is not in the domain, we cannot talk about the limit. Okay. So we can say that if I start moving towards x is equal to a on the x-axis and I'm very close to x is equal to a. I am not at x is equal to a, I am very, very close to x is equal to a. Okay. The finite value which I am getting at that point will be equal to the limit of the function at x is equal to a. Understood? Okay. So in this case, we can say that the limit of this function at x is equal to a is equal to the value of the function. The limit of the function is equal to value of the function at x is equal to a. Now let's take an example. Let's say a function is fx is equal to x plus 1. Now the function here is fx is equal to x plus 1. I want to calculate the limits of this function at x is equal to 1. Now as x approaches 1, I want to find the limit of this function. Now the symbolic representation of limit is like this. I write lim and in the subscript I like x approaches 1. This is a symbol of approaches 1. When x is equal to 1, we write it with the equality sign. But when we say that this is approaching 1, we represent it something like this. Or we can write it like this. LT, in the subscript we'll write x approaches 1. Okay. Now I have to find the limit of this function as x approaches 1. So I will write limit x approaches 1 fx, and this limit is equal to limit x approaches 1 x plus 1. Now we know that as x approaches 1, this limit will be equal to 2. This is pretty much clear. Anyone can solve that. Now let's try to understand this only question with the graph. When we see this function by the graph of this function will come like this. Okay. At x is equal to 1, we know that the value of this function will be equal to 2. Right? So, since the value of this function at x is equal to 1 is 2, as I'm approaching the value 2, as I'm approaching the value x is equal to 1, the value of the function will approach 2. Okay. Now since I am approaching x to 1, the fx will approach to 2. Therefore we can see that the limit of this function will be equal to 2. But guys, will it always happen that the limit of the function is always equal to the value of the function? In this case, we are saying that the limit of this function is equal to the value of the function. Okay. There is no difference between the limit and the value. Both are coming out to be 2. But is this always true? So let's see some exceptions when this is not true. Okay. So in the cases when this is not true, then the term limits come into use. Let's see this question. Our fx is equal to box sin x. You must be knowing this box. This is a symbol for greatest integer function. As we have already discussed, greatest integer function gives you the integral value which is lesser than the value of this function. Okay. So if I say, we will revise this one. If I say 1.2, box of 1.2, this will give you 1. So this will give you only the integral part, eliminating the fractional part of the number. Okay. And if we see the box of 2.3, this will be equal to 2. If I see the box of minus 2.3, now this is not equal to minus 2. Since I have to see the integral part and fractional part both, so this can be written as minus 3 plus 0.7. So in this case, this will be the integral part and this will be the fractional part. So the box of minus 2.3 will be equal to minus 3. Right? So I have to see the limit of this function, the limit of box sin x as our x approaches pi by 2. As our x approaches pi by 2 or as our x approaches 90 degrees, I have to calculate the value of box sin x. Okay. Now we know that when x is equal to pi by 2, x is equal to pi by 2, sin x will become 1. The value of sin x will be equal to 1. Right? But when x approaches to pi by 2, what is the meaning of approaches? When it starts moving towards pi by 2 on the x-axis, or when the value of x is very, very small, very minute difference from pi by 2. Okay, let's say this is 90 degrees. So when the value of x will be 89.99999. Okay, what will be the value of this limit? So when the value of this angle will be a bit smaller than 90 degrees, we know that this value will be a bit smaller than 1. Okay, but we know that when we deal with a box, if I have a term like 0.999 and I take a box of this will come out to be 0. Okay, so I can say that the limit of this function is coming out to be 0, while the value of this function, since at pi by 2, x is equal to pi by 2, the box of sin x will always come out to be 1, but the limit is coming out to be 0. So this is a contradiction to a statement that limit of a function is always equal to the value of that function at that point. Since we can see that the limit of this function at x is equal to pi by 2 is equal to 0, while the value